This video is meant to introduce you to a very important test for analyzing infinite series, and that test is called the ratio test. To ease our way into it, I want to do a few sort of scaffolding examples that I think will get you to understand the logic behind the test. So let's first deal with something we know. This is an infinite geometric series involving 2/3 to the n. So if you just write out the first few terms, you've got 2/3 plus 2/3 squared right, etc. So we know that this is, of course, our first term, this is our second, it's our third. Okay, so we're going to look at a few ratios here. So it says compute the ratios a sub 2 over a sub 1. Well, that's just 2/3 squared divided by 2/3, which we can see becomes 2/3. And the 10th divided by the 9th, well, that would be 2/3 to the 10th divided by 2/3 to the 9th. But again, you can see that that would just reduce to 2/3. And unsurprisingly, if we took the 100th term and divided by the 99th, we get 2/3 to the 100th divided by 2/3 to the 99th, which is, of course, 2/3. So then this says compute the ratio of the n plus first term divided by the nth term. So that would be 2/3 to the n plus 1 divided by 2/3 to the n. Now, of course, there's one more 2/3 up here. Then there's the bottom. So we can see that equals 2/3. And so if I were asked to compute the limit as n goes to infinity of the n plus first term over the nth term, well, we know that that's just the limit as n goes to infinity of 2/3. And so I clearly just get 2/3. Okay, so that might have seemed like a waste of time, but it's actually not, because it's going to lead into the logic of what we're going to do in the next page. By the way, you should note that this 2/3, right, that is the r value of our geometric sequence, right? If you think about what you have to times by every time to get to the next term, we're just timesing by 2/3, right? So that's our r value. We also know that it's less than 1. That's a key point, right? It's less than 1. It's less than 1. And since we know it's less than 1, we know that that series converges. And we actually have a formula for it, right? It's the first term divided by 1 minus the common ratio, which is 2/3 over 1/3, which is equal to 2. Okay, so I'm going to apply this exact same reasoning to a series that is not exactly geometric, but that just has sort of like a little kink in it. So for this series, right, first of all, notice it almost resembles the geometric, but that 1 over n is kind of is making it so that it's not quite geometric. If you write out the first few terms, you'd get 1 over 1 times 2/3 to the 1 plus 1 over 2 times 2/3 to the second right, etc. Okay, so now let's just compute the same ratios we were computing before. What is the second term divided by the first term? Well, so again, of course, we know this is the first term, we know that this is the second term. So the second term divided by the first term would be 1/2 2/3 squared divided by 1, 2/3 to the 1. And we end up getting just 1/2 times 2/3. So I'm actually going to leave it like that for now. And similarly, if we did the 10th term divided by the 9th, I'll get 1/10 times 2/3 to the 10th divided by 1/9 times 2/3 to the 9th. Now, if you think about what cancels, the 2/3 will cancel and there'll be 1 left at the top. And 1/10 divided by 1/9 is, if you multiply by the reciprocal of 1/9, ends up just being 9/10. So it all reduces to this. Okay, and at this point, I just want to point something out. This here, 9/10, is pretty close to 1. Which means that this whole thing is close to 2/3. Okay, it's not exactly equal to 2/3, but it's close. All right, so let's do the 100th term divided by the 99th then. So the 100th term divided by the 99th would be 1/100, 2/3 to the 100, divided by 1/99, 2/3 to the 99. And for reasons similar to the one above, we have a 2/3 that remains, and then a 100th divided by 99th is 99/100 once you multiply by the reciprocal. And once again, I just want to point out that this 99/100 is close to 1, which means this is close to 1 times 2/3, which means that the whole thing is close to 2/3. Okay, so keep that in mind. So now let's do in general. The n plus first term divided by the nth term is going to be 1/n plus 1 times 2/3 to the n plus 1 divided by 1/n times 2/3 to the n. And there'll be 1 2/3 that remains, and when you multiply by the reciprocal, you get this. Now, let's take the limit, like we did in the last page. And in the last page, remember, we got 2/3. Let's take the limit as n goes to infinity of the n plus first term over the nth term. Well, that's just the limit as n goes to infinity of n over n plus 1 times 2/3. Now that 2/3 can come out of the limit, and I get this, but I know that limit is just 1, so I get 2/3. So now it's time to reflect on this a little bit. What I've done is I'm looking at the limit of the ratio of every term divided by the one before it. In a geometric, that limit is 2/3 because it's always 2/3 wherever you are, right? Wherever you are in the geometric sequence, every term to get to the next one you times by 2/3. This series is a little different though. What this bottom computation, this limit here, is telling us is that in the long run, even though you're never multiplying by 2/3 exactly to get to the next term, as n gets bigger and bigger, this gets closer and closer to 1, which means that it's as though this series starts to behave like a geometric in which the r value is 2/3. So what we're going to conclude is that since 2/3 is less than 1, right? So we're going to use the same criteria that we used for a geometric. Since this is less than 1, we're going to be bold enough to say that means that this series, which is not geometric, converges as well. So we're treating this is like our R value, we're treating that 2/3 like our R value in the geometric. Now, the only thing we lose, and so we steal that criteria. What we lose, though, is we don't have a formula for this. Okay, so the behavior of this series is not quite as easy to analyze. We do know that it converges because we're treating this ratio here like the R value, and it's less than 1. But we don't know what it converges to. That's actually a much harder problem. So we abandoned that goal. But at least we know that it converges. And so what we've just applied here is called the ratio test, which I'll have on the next page. So the ratio test is what we basically just used. The absolute values I want you to note is just because in theory the ratio test really only applies when all the terms are produce positive ratios. Okay, so don't let that confuse you too much. But in general, I want you to view this view the n plus first term divided by the nth. View that result, and just say you get some number L. What this ratio test is telling us is if that L, which is like our R, I'm going to say like the R, you really want to view it like that. If that L is less than 1, then the series converges. If it's bigger than 1, that series diverges. And if it's equal to 1, we can't use the ratio test. It's inconclusive. And the main reason is because we don't know whether the limit is approaching 1 from below or above. And that makes all the difference in terms of whether or not that L is behaving like a R value that's less than 1 or bigger than 1. Okay, so this is the ratio test. We're going to look at some more concrete examples in the next video.